session before lunch. All right, so now we have Micah Blake McCurdy, who will talk about skater impact on shot location. So Dr. Micah Blake McCurdy earned a PhD in mathematics from Macquarie University in Sydney, Australia, and he is the founder of HockeyViz.com. So welcome, Micah.
Thank you all very much. So this talk is one of the more straightforward of all the talks that I'm ever going to give. It's sort of just what it says on the tin. My talks are routinely not straightforward, so you're all in for a treat. So I'm trying to measure exactly how much influence do individual skaters in the NHL have on where shots are taken on the ice. Simultaneously, how many shots and where are they from? This is and I'm going to measure how much it is, and it's actually quite a bit. It's great. So many of my talks have, so here's an interesting thing, how they can say, oh, it's actually very close to zero, infinitesimally close to zero. This contains correlations which are not infinitesimally close to zero. You will all be delighted to hear. That's me, that's my website. You can go there. If the talk is really boring, you can find pretty things on the website. So, the central question of analysis is always, what do we expect? Every time, all the time. What do you expect? And as part of that, given what you expect, how do you explain the variations between what you expect and what you see, and whose fault is it? Or whose credit is it? Or, not to be too hard-nosed, but if we have a bunch of players playing ice hockey, and something happens, who is responsible? That's and statistical tools in some sense, in some very broad sense, are designed to attack this. And part of why I decided to look at this question about shot locations. This is what we're going to do in this talk. We're going to try to isolate player impact. Isolate it from what? We'll get into that in a second. Consolidate that impact into some convenient units that we can understand, and then measure the correlation from season to season to get a proxy for some sort of skill. If people are able to do something, they should be able to do it consistently. Especially if we're able to isolate their own contributions from the factors of other people and context around them. So you can judge for yourselves how successful I am at that. Why did I decide to look at shot locations? Why this particular problem? And there's two reasons for this. And they're two sort of seemingly contradictory lines of thought that come from two directions. One is that we know empirically, intuitively, but also empirically, we know that the shot location affects how likely a goal is to go in. If you shoot from dead set in front, you have a very high chance of scoring a goal. If you shoot from the other end of the rink, you have almost no chance of scoring a goal. We know this intuitively, and you see it empirically. In fact, you can measure very, very carefully what the probabilities are, and many people have done so. But on the other hand, we know that the probability of a given shot being a goal depends very, very weakly, possibly not at all, on the individual skaters who are on the ice. It depends consistently on the goaltender, but it doesn't, well, even that's a dodgy bit of business. We won't get in. There are no goalie stats in this talk, just so you all feel safe, just so we can all be psychologically safe. My last talk was about goalies at a different conference, and I still haven't recovered completely. Yeah, right. And so we know that players, in aggregate, have no discernible statistical influence on the performances of their goaltenders. But we know that shot locations do matter. And so there's an interesting question, is where is the disconnect in between those two things? And in particular, how do we go from individual player performances, shot locations, shot results? So specifically, I thought, well, let's look at that first piece, and let's just answer the very simple question, how much of the shot location information can be determined from specific players and their isolated impacts? So, this is a small digression into regression as the statistical tool. So I'm assuming that some of this will be extremely old hat to many of you, and some of it will be new to others of you. And part of why I'm going to rehearse something that you could find in any textbook is because I'm going to do it in a slightly bizarre way. So, and it'll be crucially vague for large stretches. That's important, so bear with me. So let's say you have some list of observations, alpha, that you collect about ice hockey players. In fact, at this level of generality, it could be about crop yields. It could be anything you like. So you have a collection of observations, and you catalog them all, you write them down. So-and-so, 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 these things happened. So-and-so, 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 these things happened. You write them all down and you put them in a big matrix and you call it alpha. Then you have a design matrix which just encodes who was on the ice at the particular time. And in fact, in some more general sense, it encodes all of the things that you're interested in. So, and each row of your design matrix contains a specification of the things that prevailed, the circumstances that you're interested in that you recorded. And then each matching observation alpha is what you saw when those conditions happened. And then beta is and this is the part where the imagination comes, and this is the part where your intuition comes, and you say, I'm going to associate with each of my variables, and associate an imagined capability or quantity or quality. But it's like, imaginary here is crucially important. Right? This is where the modeler is saying, I think there is a thing here, which I'm going to call beta, and then I'm going to somehow try to get a hold of it. Right? And so in this case, what we're going to try to do is we're going to have a collection of observations that's going to be about shot locations. The design matrix is entirely going to be based on players and who's on the ice at given observations, and beta is supposed to be individualized impacts on shots. So that's what we're trying to get a hold of. And so you write it down as a mathematical equation like this. It looks very simple, because that's what matrices are for. They're designed to high complexity this way. We invented them for just such a purpose, and they're very good at it. And so the question is to solve it. The trouble, of course, is that in practice, this matrix X is extremely tall and not very wide. So you have only a handful of players that you're interested in. If you're looking at NCAA hockey, like in the previous talk, then you're looking at not very many players. Even in the NHL, you have not that many extra players, but the number of observations, the number of different circumstances you have to consider is very, very, very large. So what you do in this case, so this is only the simplest of regression techniques that you could apply. And I'm going to walk you through it because you'll just see why. I'm going to walk you through it momentarily. What you normally do in this case, in the general case where you have an overdetermined system where you have way more observations than you have individuals, which is the standard case. So in this case, each observation corresponds to a subset of people, and the number of people you have on the rink is the number of columns. So we're looking at say something like 20 or 30 columns, for instance, if we're looking at a single NHL team for a single season, and the number of possible combinations of 5 of them at a time, if we're looking at purely 5-on-5 data, which is what this talk is entirely about, is many thousands. So this matrix you should think of this matrix X as a very, very, very narrow, extremely tall skyscraper. So you multiply it by its transpose, that makes it considerably smaller. In fact, in particular, it makes that matrix on the left-hand side square, and in general, invertible. So you just invert it. Multiply it by both sides, there's your beta. So this has been your extremely quick and really, really shoddy first year statistics. I've never taught statistics, can you tell? Yeah, I'm a mathematician by training, I get to say these things. So, but here's the crucial detail, and here's the thing which is really interesting. So this little argument that I ran you through is not a proof. This beta obtained in this way is in some sense the best possible estimate of beta, and you can prove it. You prove that it minimizes a particular measurement of error. That proof goes through even when the elements of your observations and the elements of your skater skill components are not numbers, but elements of any inner product space. This is the sort of thing that you do when you're a mathematician, is you think, how can I generalize these extremely simple things to crazy settings? Here, I mean, any inner product space is not the craziest setting in the world. But now, instead of having single numbers, so this person's ability is 5.4 of some units that I just made up, instead, I'm going to take the elements, my observations, of alpha and beta to be functions. Functions defined on a hockey rink, whose values are the relative likelihood of a particular shot being taken by a particular player at a particular time. This is an inner product space, the obvious inner product. You just take, if you have 2 of these, you just smush them together by multiplying all the pieces, piece by piece, and then you add them all up. You have to check it's an inner product space. It is. You have to check that it does the right thing with regard to error terms so that the least squares regression that I just talked about goes through the way you want it to. It does. It's the sort of thing that as soon as you have the idea, there's sort of no work to do. So my observations are going to be maps like this. And this is an example I chose. This is what happens. This is the way that Ottawa shoots the puck when Erik Karlsson is on the ice at 5-on-5. The red regions are places where the Senators shoot more. This is just this past season. In fact, the data I'm going to show you, the correlations I'm going to show you later are for many, many seasons. But this is this past season. Red means that's where they shoot the puck more. Blue is that's where they shoot the puck less than league average. The numerical units associated with these color intensities are not interesting for us today, but I can tell you if you really care. So what you discover is, so first of all, you discover that there's a lot of red all over the rink. They just get more shots. Second of all, you notice that there's not a huge number of shots in the slot, especially not on the left-hand side of the slot. That's where they're shooting less than league average. You can also see Carlson himself. Most of those shots there are him. That's his position, right defense. He's, I think you could safely say that the enormous bulk of the Senators' shots from that location are him. Probably all but one, just a rough guess, for an entire season. Also, you see that there's plenty of shots being taken right in the net front. So those are not him personally. So this is just him on the ice, but it's for the whole team. In fact, the sort of 5 hotspot locations are reasonably well defined. They're almost certainly the left wing, center, right wing, right defense, left defense. Pretty much. And so I mean, these observations are great fun. You get to pick them apart. Certain players are really interesting. In particular, you see that not only is he personally taking a lot of shots down here, but also the right wingers are taking more shots than the left wingers. Much more shots than the left defense. You can start to get an idea of what kind of offense you're talking about. But then the question is, how much of this is due to him? So this looks great, all this stuff. You know, shots in here are nice, but shots in here are better. How much of that is because of Carlson? And how much of that is because of the other players? So the idea is we want to isolate a player. So I chose Carlson just because everybody loves Carlson. But we want to isolate. So there's 2 things we're going to isolate. We're going to attack with this technique that I described earlier. One is we're going to look at attacking teammates. Quality of teammates, specifically who you're deployed with, is the single most important contextual factor that affects individual player results. And we're also going to try to account for where players begin their shifts. If they begin their shifts in the offensive zone, obviously they get better numbers. That, in some sense, is not their fault. Right? They're being given a small head start by their coach, and so that has to be taken into account. And some players, like Carlson, for instance, start, because they're known to be offensively skilled, start a larger proportion of their shifts in the offensive zone than you might expect. So let's see, how are we going to actually get a hold of that? Well, so the standard approach, of course, is to take this equation here and just work it out with a computer. That's a matrix. It's not that big. We have big computers, as I like to tell people, they're cheap. Just work it out. That's a matrix you already know. Just take its transpose. Alpha of those are observations you already took. Just do it. Computers we made them for this reason. However, it's easy enough to say, well, we're just going to do this numerically. But it's not so straightforward when the gadgets you're putting in aren't just simple numbers, but elements of some complicated inner product space, where when you're going to do that calculation numerically, it's suddenly very, very elaborate. However, in this case, when we set this matrix X to be this particular matrix, where its columns are all of the players on the team, and the rows are all of the combinations of all of the players taken 5 at a time, you can do it by hand. You can do it with a pen and a paper, and a lot of patience and coffee. And it turns out to be extremely simple, which is extremely satisfying. This is another sort of thing where the mathematical background comes in handy. Many, many hours spent in pubs doing long proofs like this. And in particular, the estimate you get for beta is 5 times the average result of all of the observations when the player is on the ice, minus 4 times the average result of all of the observations which don't have the player on the ice. And this is, if those numbers 5 and 4 seem interesting to you, it turns out that the proof can be generalized completely. In fact, I've published this, you can read it if you like. It's an extremely small and not especially enlightening piece of combinatorics. You just write down a whole pile of binomial coefficients and then you hit them with a stick real hard until they give in. And which is, and forgive me, but that's sort of what a lot of combinatorics is. My discipline, hockey is my full-time day job now, but my old discipline is the least useful part of mathematics ever. So of course I celebrate this by taking pot shots at all the rest of mathematics. But it turns out that, so this 5 is entirely because there are 5 people on the ice. And this 4 is 1 less than 5. if the game were played 10 aside, then this formula would come out as 10 and 9. If there were 100 people on a side in some beautiful, beautiful future, then it would be 100 minus 99. The proof is complete. And in fact, you can also, if you want, you can rewrite it and say this is alpha with p minus 4 times the difference of what the team does with you on the rink and what it does without you on the rink. It also has some nice properties. For instance, if the results are the same, with you on the ice and with you off the ice, then what you get from this is that common value, which is what you would expect. Your impact is exactly that. So it passes the smell test also. And so once you have this, you say to yourself, okay, that's great. Now how can we, if we imagine that this is isolating from teammates, that's how we designed our matrix X was to account for teammate correlations. There are some weaknesses there, which we'll get into in a little bit about what things it doesn't do, but on its first glance, it does that. We'd also like to handle deployments at different zones. So one of the things we can do is we can make estimates of these things, one for each zone that you start in. There's only 4 different ways you can start a shift in the NHL. You can start in the neutral zone with a face-off, in the offensive zone with a face-off, in the defensive zone with a face-off, or you can just jump over the board in the middle of play. I mean, those are the only 4 choices. You literally cannot start a shift in any other way. And also, some previous work of mine, which I won't reference here, shows that those 4 cases, that there's no sense in breaking those cases down anymore. Especially not the on-the-fly ones. There's no useful information you can scratch from, at least from the data that we have now. There's no way to distinguish interesting things from that. So we can just we just pretend that shifts started in those 4 ways are actually 4 different players. So we take our 20 players and we multiply that artificially by 4. And so I might have some metric for Matt, and then I might just break it into 4 metrics. Matt starting in the neutral zone, Matt starting in the offensive zone, and so on and so forth. And then I can just take them all and put them together with coefficients. And those coefficients are not taken from observations about one particular player. Those coefficients are taken from the league average. So the league average is 17% of your shifts start in the neutral zone, 13% in the offensive zone, 11% in the defensive zone, and 59% on the fly. This has come up before. Most shifts in the NHL start on the fly. And also notice that it's not symmetric. 13% in the offensive zone and 11% in the defensive zone. There's no reason for that to be symmetric, because just because you start your shift in the offensive zone, that doesn't mean the other guy on the other side of the puck is starting his shift. He might be continuing his shift. She might have been on the ice for 20 seconds already and got pushed back into her zone. And now your coach thinks that they're going to take advantage of that. So she's not starting a shift, but you are. And in fact, coaches in the NHL show this tendency. They prefer to change in the offensive zones. There are more offensive zone starts than there are defensive zone starts. Just a curious little tiny but interesting insight into coaching. So this is what happens if we take Carlson and we break up his data into 4 pieces. This is what happens when he starts in the defensive zone. Not as many shots. Turns out it's not so easy to get shots when you have to go the entire length of the ice. The neutral zone, again, a little bit depressed, but starting to see 1, 2, 3, starting to see these little pockets. He personally taking these shots. On the fly, even more shots. Typically on the fly, starts to generate more shots, both for your team and also for the other team. That's the neutral zone. You have to standing stop. There's something just about speed there. And the offensive zone, now when you start in the offensive zone, you see this huge preponderance of his own shots in the corner there. And starting to see that pattern emerging. Those situations are all extremely similar, and also the Senators, without him, which is what most of that data is, are a very, very ordinary team. So you get very, very plain, hardly any profiles at all. And so then when you isolate his particular shot impact, and that's defensively. Not so great when he starts in his own zone, much better when he starts in the other zone, exactly the same logic as previously inverted. And so then when you isolate them, what you get is something very interesting. Again, you still see quite a bit of red ink on both sides. You see in his own zone, you see his defensive impact is he causes shots to be taken on the other side of the ice. So when Carlson's individualized, isolated impact is that his side of the ice is well defended and the other side of the ice, not so much. Also you notice that now that it's isolated, there's considerably fewer shots in front of both nets. The defensive impact here is a little better than the weakness of the offensive impact. And this has partly to do with the coaching system employed by Ottawa last year, and it has something to also do with the fact that we've taken out his actual zone starts and replaced them with what we expect, going back to what I said was the central issue at the very beginning, what we expect to have if he were given, not the starts he was given, but league neutral starts. We're trying to isolate impacts that are the same for everybody. So that's very and everybody loves pictures, but if we want to measure correlations, strictly speaking, we can measure correlations again in any inner product space, but this inner product space has an extraordinarily high dimensionality, and so any correlations you calculate on it are going to be ludicrously small. Also, our intuitions about what correlation sizes are all wrong because they're all tuned by R, by the real numbers, because that's where we take all our correlations. So maybe I could rescale them for you, only I don't have any intuitions for that stuff. So instead, we're going to try to isolate, we're going to try to condense this into a single number somehow. And the way that I'm going to do that is by ignoring shooter and goaltender quality and isolate only the effect of the quality of the shot locations itself by weighting these things, by taking a weighted average of this picture by league average likelihoods of goals. Of shots. I should have said earlier on that these shots are all unblocked shots. So they're not shots in the sense that they're all shots which are either misses, saves, or goals. So anytime you take a shot and it gets at least somewhere close to the net in the eyes of an NHL stat recorder, this is what we're coming up with. And so everything needs a name, and so I decided to call this thing threat. So this is your isolated threat. And the units are nice, they're goals. They're expected goals. I call it threat instead of just calling it expected goals, because an expected goals model by now, even hockey is still reasonably young in terms of what its statistical sophistication is, but already we expect, a quote unquote expected goals model to include a number of other things that I'm not talking about here. But the units are still goals. That's because this was not designed to be an expected goals model that was supposed to be like a war-like or a GAR-like stat. It's supposed to specifically laser in on shot location isolation. And so in particular for Carlson this year, you see so his threat for is 2.4 goals per hour, and his threat against is 1.3 goals per hour. So that's what you can expect his individual impact to be. In particular, the regression means that some people come out negative. Some people, which is surprising, some people actually take away goals from their team. Some people take away goals from the other team. This is great. So Carlson is going to give up these goals, but also give you back those ones. And then, of course, the coaches can tweak that by actually deploying them in particularly different ways. For instance, offensively, as they do. And this is what you actually see. In fact, it was worse than that. And the actual with him on the ice is, of course, affected by many other players, not just him. So what are the correlations? So these are my last 3 slides that just display the correlations themselves. I looked at individual seasons of players with particular seasons over the course of the last decade. Purely in terms of offensive threat, the correlation is reasonably strong for social science data like hockey, 0.34. Defensively, on the other side of the puck, surprising to me, it's considerably weaker. Defensive performance appears to be considerably less correlated with itself from year to year than offensive performance in this. This is perhaps highlighting a well-worn truth that people are better at evaluating offense than they are at evaluating defense. But what is more interesting to me is that, in complete contradiction to some of my previous work, the net difference between them has a considerably stronger correlation year over year, which suggests that perhaps there is some truth to the old line that players adapt strongly to the roles that they're given, and in a given year might play in a particular style, and in a given year following might play in a different style, which is where the defensive and offensive profiles are different, but the net difference is not. This I don't completely understand. But 0.46 is, as hockey data goes, is pretty high. Also, you'll notice there's a slight positive bias. The point in mode is actually up here a little bit, especially when you weight these correlations. Oh, and these correlations are all weighted correlations. They're all weighted by the number of games that these individual players played. So some of these crazy outliers, those are only a handful of games each, and so they're weighted suitably. And so the conclusions are that they have small, 0.46 as a correlation goes is not enormous, but it's small, but definitely noticeable, individualized effects on shot locations that you can detect this way. And those effects are strongest when you consider net threat and not merely offense or defense separately. So these two things need to be held in tandem. So there's lots to do in the future. Interactions need to be isolated with goaltending. I carefully kept goaltending out of what I was talking about here, but ideally you'd keep them separate, but then you'd have them both. Shooter quality, there's no attempt been made for shooter quality here. Quality of competition, we know quality of competition is much less important than quality of teammates, but it still should be accounted for. Score state, if you're winning or losing, is also extremely important, especially winning or losing at particular times. There's no attempt here so far for coaching effects, no nonlinear effect. The model that simple least squares regression that I told you about is purely a linear model. Nonlinear effects might well be interesting. But that's all I got. Thank you very much.
I guess with the correlation of the defensive effects, do you think the coaching might be something intriguing there? Like, you know, Pittsburgh last year in their playing style, how much it changed from Mike Johnson and Sullivan, and something that could really cause that variation.
It could. So I'm torn about this in a couple of ways. On the one hand, if coaching had a strong, consistent impact on the way skaters played, we would expect correlations to be higher, because we would expect people to play as their coaches asked all the time, so that doesn't fit with my intuition about coaching as being reliable and repeatable, because I've seen the most heavily coached aspects of the game being less reliable and repeatable. So that's one confusion. The other confusion is there could be, in fact, I think we have some anecdotal evidence of this at least, there could be very strong survivor bias in the interaction of defense and coaching. People who don't do as they're asked defensively by their coaches don't get minutes. They fall out of the league, in fact, really fast. And in fact, I think the survivor bias here is considerably stronger than what you would expect from a pure skill ice time interaction. I think there are cultural factors here that are sharp in that interaction. And so those two things together kind of make my statistical intuition about that a little wonky. So I don't know how that's supposed to turn out. Yeah. This is one of those things, I tested this on a couple of nerdy friends of mine where I just told them what I did and I just said, I want you to guess the correlations of those three things. After I had basically I gave them the whole talk and then I said, and now here's the 3 conclusion slides and I want to hear what your numbers are. And I got 5 totally different answers from people, all of whom I did and still do respect. There's a lot of, there's a lot of, what is intuitive and what is not is for braver souls than me, I'm afraid.
A little bit more time, any other questions?
Yes?
In looking at the correlations, do you break it up into the zones that you're talking about, the way that their shifts started?
So I imagined to myself that I had isolated in this calculation here where I took all of those and averaged them in that league average way. I hoped that I'd taken that out of the equation, as it were, that I'd obtained a sort of zone neutral thing. I suppose I could have, and so the values you see are the threat things taken from this calculation. I suppose what I could have done is I could have instead of aggregating them with that weighted average, I could have just thrown them all in the correlation. Like I could have had, instead of having this 1 dot, I could have had 4 dots for him. And I guess then I should have probably separated into 4 correlations and worked it out for 4 different things separately. You know, this is what players offensively deployed do. You know, in fact, that might be interesting because you could see some qualitative distinctions between the 4 different plots. You'd see, you know, people who get lots of offensive things, they are good at offense. Their coaches are isolating that correctly. But no, I didn't. I didn't think I needed to do that because I thought I had done it. I thought I had sort of tackled it here. But that would be interesting to look at. In particular, it would tell me if I was right to have done it.
Yeah.
Which would be valuable.
It could be an interesting application to like power play as well. Like as far as alignment, say from Pittsburgh area, so you know the argument is Crosby on the half wall or down low, and seeing maybe the difference in performances positionally, or you know who you have on the ice.
Yeah, you definitely could. There'd be, I mean, you'd run into some of the problems that, that you'd expect. That you'd have less data, you'd have less time, you're sort of me being blithe about coaching effects would definitely not fly anymore. You know, because power plays are ruthlessly coached, and so are penalty kills, right? And those 2 interactions are really important. But yeah, it would be fun to dig into that somehow.
See if Brent Burns is killing San Jose power play.
Yeah, right. I have my doubts.
All right, we got time for one more question.